Okay, solution phase reaction. A solution is a homogeneous mixture. It has uniform properties throughout. That is, the distribution of solute in that solvent is uniform throughout the entire mixture. The composition of a solution is a solute plus a solvent. The solute is the component in lowest amount, and the solvent is the component of the solution in greater amount. And it's pretty easy to visualize. It's like taking a spoon of sugar and pouring it into an 8-ounce glass of water. Well, the sugar would be the solute, and the water would be the solvent. You stir, eventually the sugar would dissolve and have a uniform concentration throughout the solution. So that leads us to how are solutions defined. They're defined in terms of, in this case, concentration terms. Concentration of solute in solution. And I'll abbreviate solution as given right there. Concentration terms, CONC, by definition is the amount of solute in an amount of solution. Now, that is the two components of the solution, solute and solvent in the denominator. And that comes into play in in many problems, but we're not going to deal with that right here. The one that we're going to deal with in terms of concentration of solute in solution is a term called molarity. And it's defined as or symbolized with a capital M on a solution. And molarity is moles of solute in a volume of solution expressed in liters. So it's moles per liter. Molarity is moles per liter. It is not moles. Moles is the mass of one formula weight. It contains Avogadro's number of particles. But molarity is like a density number. It's a mass number per unit volume type number. And it's the distribution of the solute in the solvent. Example would be, say, a 1 molar sodium chloride aqueous solution. See, that's the symbology. And AQ refers to it, the solvent as being water. And then, of course, you have the salt, table salt, dissolved in the water. This would be 1 mole weight sodium chloride dissolved in 1 liter of solution, not solvent, solution. Because if you just took the moles of NaCl and poured on top 1 liter of solvent, it'd be too dilute relative to what you're trying to make or whatever you're trying to define. But this is the average definition. Okay, so we're talking about a 0.5 molar HCl aqueous solution. That would be 0.50 mole HCl per liter of solution. So it's moles per liter. And when you look at the terminology that's given, it's always in terms of how much solute is in solution. Okay, now, when data comes to you, it'll come to you in the form of solution data. And this solution data relates to a reaction that's going on in solution. and you need to take the solution data, bear with me, solution data, and convert it to moles of solute. So how do you do that? All right? By definition, molarity of the solution, which you got to say a 0.5 molar, a 0.25 molar, or 1 molar, whatever molarity solution, is equal to moles of solute per volume solution expressed in liters, right? Moles per liter. Moles over volume in liters. I want everybody to catch up and listen to me. Everybody got that? Solve that expression for moles of solute. You multiply both sides by volume of solution, don't you? Isn't that what you do? So moles of solute is equal to molarity of the solution times volume expressed in liters. A combination of molarity and volume is referred to, when they come to you in data, is referred to as solution data together. Now, sometimes solution data comes in molarity and milliliters. But if you're going to get the moles of this solute, you have to mentally know how to convert milliliters to liters, divide by 1,000 or move the decimal over 3 places. And then multiply by whatever given molarity you have, and you have the moles. Now, the moles of solute would be the reactant. One of the reactants in the reaction. And let me show you some examples. Of how solution data looks. Comes to you. Once you understand this, then you apply it in the same way we've been talking about. Okay, so if you look at this problem right here, it says, what volume of 0.250 molar of nitric acid reacts with, now watch, 44.8 milliliters of a 0.15 molar sodium carbonate. You see that you have a volume number along with a concentration number like that. That's solution data. If I multiply the concentration number times the volume number expressed in liters, I have the moles of that compound. So molarity times volume in liters gives me the moles. And once I get the moles of that, then I know how many moles will react with that one, or how much yield will be. And I'll show you in a minute. Here's one. The next one is, now this one is given in grams of one of the reactants. Here, I think, let me find it. It was, yeah. Let's see, no, this. You've got a flask contains 49.8 milliliters of a 0.15 calcium hydroxide. That's solution data. Multiply those two together where volume is in liters and you have moles of calcium hydroxide. How many milliliters of this molarity sodium are required to react completely with the calcium according to this reaction, like that? So you have moles against moles. And this is molarity times volume, which will give you the moles here. Molarity times volume. Well, those are equal because they have the same coefficients. Molarity times volume over here. Doesn't that give you moles? That's what we just solved. And molarity times volume. Here's one. Oh, that's in grams. This is the one I was looking for. So you have a 0.150 molar sulfuric acid solution and against 8.2 grams of sodium bicarb or sodium hydrocarbonate. Well, if you got 8.2 grams of sodium hydrocarbonate, how do you get it to moles? You divide by formula weight. You know how to get the formula weight, don't you? So you figure out the formula weight and divide it into 8.2. That's moles here. Well, how does that relate over here to moles? Half as much. So if you double this one, you can set an equation in here. You can say molarity times volume, 2 times molarity times volume equals molarity times volume over here. And that's the thing I'm trying to teach you. These are solution phase reactions. And I'm going to give you one that's a little simpler than some of those right now. But molarity times volume is moles. That's your conversion. Now, I gave you a handout at the beginning of class on what you can calculate from a chemical equation. And at the bottom or somewhere in there, it talks about solutions. And it says convert to moles. How do you do that? You back to that. Multiply molarity times volume. Okay, so let's say you're given the following problem. 60 milliliters of a 0.125 molar sodium hydroxide, a sodium hydroxide solution, aqueous solution. How many moles of NaOH are in solution? Okay, what are you looking at? You see a volume number and a molarity number. Those are combined in solution data. Well, we know that moles is equal to molarity times volume expressed in liters. So this one would be 0.125 molar, which is moles per liter. And that's times, well, I'm going to have to come down, times 0.060 liters. Because liters drop out and you're left with moles. See that? Hopefully. You'll see that down here. So you've got a mole number there. And if you got another solution that you're mixing in with it for another reaction, I mean, 2 reagents coming in, you're getting a reaction out of it. And so you work your problem in terms of moles and figure out what the yield is. Okay, here's a... Okay, jot that down. What it's showing you is sodium hydroxide aqueous. That means you've got an aqueous solution of sodium hydroxide. You've got an aqueous solution of hydrochloric acid, and you're going to mix those two together. And you're going to make some sodium chloride and water over there. Now, if they mix equally, 1 to 1, we'll have 1 mole of sodium chloride. So if I know what moles of sodium hydroxide and moles of HCl, then I can figure what the moles of sodium chloride, because it's a 1-to-1 reaction ratio. Everybody good? Just on the fundamentals. So whatever I'm given, I need to convert to moles, right? Okay, so let's say you're given 25 milliliters of a 0.12 molar sodium hydroxide solution. And you're going to mix that with 30 milliliters of a 0.095 molar hydrochloric acid solution. Right there. What's the limiting reagent? How much excess after reaction stops. One of those is going to be an excess, right? Because one of them is limiting reagent, it's gone. Okay? And how much you can define this in moles or grams. Once you get to moles, you times the formula weight. How much NaCl will form. Okay? So in the section on stoichiometry of reactions, I said convert to moles and then solve the problem. Or get the limiting reagent and then solve your problem based on the moles given. Okay, so to get the moles of sodium hydroxide is molarity times volume in liters, right? I can do that. So I can get moles of NaOH is equal to molarity, which is 0.12 molar, times the volume in liters, 0.025 liters. .003. Now the moles of hydrochloric acid now are equal to molarity 0.095 molar times 0.030 liter. Just move the decimal 3 places to the left. .00285. Since we're splitting hairs. So in that, since they're both the same coefficients, we divide by 1, and then the smaller number would be the limiting reagent. So the hydrochloric acid is the limiting reagent. Everybody good up to now? Still with me? Okay. Now, the reaction ratio is 1 to 1. So if I have 1 mole of hydrochloric acid, how many moles of sodium hydroxide am I going to use? 1. If I have 0.00285 limiting reagent mole of HCl, how much of this am I going to use? The same number, right? Same number, yeah. Okay. So to find the excess, I simply subtract that 0.0285 mole used of the sodium hydroxide, because it's going to be the one left over, right? Everybody see that? You see the point? Everybody good? Sure. Because that is a difficult point sometimes for students, to see that who's left over and how much. Well, it's amount used, and it's always coming out in excess. So when I subtract those two, I get 0.00015 mole sodium hydroxide in excess. Now, the last question in here is how much sodium chloride will be formed. Well, it's based upon the limiting reagent right here. So if I have the moles here as the limiting reagent, right there, then the moles of sodium chloride will be also 0.00285 mole of NaCl, because it's a 1 to 1 also. See the point? Very important type of deductive process as we get deeper, especially in Chem 2 if you go there. So your amount of sodium chloride is, of course, the 0.00285. Okay? And so on Monday, I'll demonstrate this and show you how to do it, and then you'll go repeat it just for reinforcement, but it will be just like what we showed you in the lecture. And here we'll have the sodium hydroxide aqueous solution, and this will be a known concentration. And you'll be adding it into a specific volume, given volume of HCl solution, but unknown concentration of HCl. And so you will know the concentration up here. If you can determine how much volume you need to add to reach neutralization, now I showed you earlier, you start adding, and the sodium hydroxide is a limiting reagent until you react out all the, well, it was red dots into purple dots, remember? All right, when you hit everything's converted, that's where you can determine what the moles of this is. Molarity, you're given. Known concentration. Known molarity. And if you measure the measured volume of sodium hydroxide solution expressed in liters times that will tell you the moles that you neutralized. See that? Because molarity times volume is moles. Okay? And this will be, of course, an HCl, let me do it the other way. NaOH plus HCl goes to NaCl plus H2O. And so what you're doing is adding sodium hydroxide to the HCl solution until both of these are gone and all you have is sodium chloride. Well, you'll be able to plot that, and I'll show you on what we call a Lagerpro vernier system. And you will generate a titration curve using a pH electrode to monitor this. So you will have an electrode, a pH electrode in here, monitoring value. It'll be a number there. pH, many of you have heard of pH before, but pH 7 is neutral, below 7 is acidic, above 7 is basic. Maybe you know it, maybe you don't, but that's okay. So when you put the electrode into your acid solution, you'll be down here low, and this will say that's the 7. And then you'll start adding that base in here and neutralizing the acid, forcing the pH upward. And what you'll observe, and I'll demonstrate it, is a trend that will look like this. And at the equivalence point, this will run through very quickly, or the neutralization, and you'll generate a curve just like this. And this point right here at 7, and right here, this tells you the volume at neutralization. When it neutralizes. So you take that volume right here, that's your volume of neutralization of your times your known volume. Once you multiply that times your known concentration, you get the concentration of your acid. And that you should mentally relate back to what we've been talking about for the last 2 lectures in terms of numbers. And it's very straightforward. And we'll go through this, and it won't take long to go through it. But come here first, and let me do preliminaries, and then we'll move to the lab. It won't take long to do that.